is example 3 from your 10.3 to 10.4 packet, and the measurements of CQ and CR are both 3.2 centimeters. So my hypothesis is that they're both equidistant from the center of the circle. So since chord ML is congruent to chord PN, that means their distance to the center of the circle must be the same. The proof of that is very short. We can draw in these two radii, which are congruent to each other. And since this CQ goes through the center of the circle, we can extend it into a diameter, and since it's perpendicular to that, it bisects it. And same thing over here, CR is perpendicular to PN, so it must be bisecting it. PN was equal to ML, so through a series of segment addition postulate, transitive, subtraction, we can get those two segments congruent to each other. We already have the right angles in those triangles. So then through a hypotenuse leg, the triangles are congruent, which means that CR must be equal to CQ. Number 4, this is an interesting one. Angle DCE is called an inscribed angle. Its vertex is on the circle itself. In other words, this is kind of like an inscribed polygon or inscribed triangle if we were to connect segment DE. So we have this inscribed angle DAE as a central angle. They both have the same endpoints of D and E. The measurement of angle DCE is 43 degrees. The measurement of angle DAE is 86 degrees. And so my hypothesis is the measure of this inscribed angle is half the measurement of the corresponding central angle. This is kind of a neat one. If we draw in segment DE and segment AC, then we know a few things. There's 3 isosceles triangles in here. Since these two segments are equal, these angles are both X. And since AC is equal to AE, I can call both of those angles Y. And since AD is equal to AE, I can call both of these angles W degrees. And at this one in the middle, I'll call angle V. So one of the things I know is that in this entire triangle, all the angles are going to sum up to 180 degrees. So then looking at those angles, it's X plus W plus W plus Y plus X plus X. All of those added up together equal 180. So I see there's 2 X's plus 2W plus 2Y equals 180. And that's all of the 3 angles that make up that yellow triangle. And if I divide everything here by 2, X plus W plus Y is equal to 90 degrees. Next step, look at this triangle. And it's another triangle, so I know the 3 angles in that triangle add up to 180. So 2W plus V is equal to 180. And if we solve this equation for W, we get that W equals 180 minus V divided by 2. That'd be 90 minus V over 2. Then we can take this W, plug it in. Now it's X plus 90 minus V over 2 plus Y is equal to 90. Subtract 90 from both sides, add V over 2 to both sides. X plus Y equals V over 2. In other words, X plus Y, this angle down here, X plus Y is equal to V divided by 2. Half of V is equal to that. Or double this angle to make it equal to that. Number 5, put point H on this circle. So here is my point H. Draw in those 2 chords and measure angle GHF. It turns out that that measurement is 90 degrees. So an inscribed angle measures 90 degrees like this one if and only if endpoints form a diameter of the circle. And for this one, we don't have an informal proof. I'm just asking for a reason. And what we know is that since this is an inscribed angle, it's equal to half of the corresponding central angle. So if I take the 2 different sides that make up this inscribed angle, trace them till the end, they end at points F and G. That means that this angle right here, this yellow angle, is half the corresponding central angle. The angle that starts at G goes to B and to F. So I'm talking about this entire angle, which is 180 degrees. Divide that by 2, and we're always going to get 90 degrees no matter where that point H is at. Next one, find the measurements of these 2 angles. Well, it turns out they're both 49 degrees. So this angle is 49 degrees, that angle is 49 degrees. I see that they're the same. So I have these 2 inscribed angles, angle JKI and angle JLI that are equal to each other. If they have the same endpoints on the circle, then they are equal. If we look at angle JKI, it goes to that arc angle. I don't know where the center of the circle is at. I'll just say it's maybe about right here. This angle 1 is 1/2 of that blue arc angle because it's corresponding to that central angle. This angle 2 is also 1/2 of that blue arc, which is that central angle. So since 1 and 2 are both 1/2 of the same central angle, they have to be equal to each other. And then for the last one, we have this quadrilateral that's inscribed inside of a circle. We can measure all the angles. And interesting thing happens here. I'll call this X degrees. And this will be Y degrees. And together, I know that since that makes up the entire circle, that X plus Y is equal to 360. Now, if I look at this angle K, K ends at point J and point L. So, since K is an inscribed angle, it's half as big as its corresponding central angle. And I don't have the center of the circle in here, but wherever the center of the circle is at, it would end with this arc. So half of this arc is equal to K. So K equals 1/2 X. And then going over to the other side, here is angle I, ends at points J and L. So then the measure of angle I is 1/2 of Y. We add those together, the measure of angle K plus the measure of angle I equals 1/2 X plus 1/2 Y. And if we simplify that just a little bit, the left side can stay the same. The right side, we can factor out the 1/2. So K plus I is 1/2 of X plus Y. From earlier, we know that X plus Y equals 360, so 1/2 of 360 is 180. In other words, angle K plus angle I are going to have to add up to 180 degrees. So the opposite angles in an inscribed quadrilateral supplement. We could have done the same things for angles J and L, and they also would have been supplementary.